Hello everyone. Today we discuss about qualitative analysis. It's a salt analysis where we have to identify acidic and basic radical in a given salt. Acidic radicals are that one is an anionic part of a salt. For example, carbonate radical, nitrate, chloride. Whereas basic radical, that one is cationic part of a salt. For example, ammonium, lead, aluminium. If you just recall our grade 10 concepts, like a chapter acid, base, and salt, where we did how to identify the given acid or a base in a salt. Like, suppose I'm taking an example of lead nitrate here. So, this lead nitrate, it contains lead ion and nitrate ion. Lead ion, it comes from a base part, and nitrate, it comes from a acid part. So what we do, in case of base, we add on hydroxide part, so it becomes lead hydroxide here, and in case of acid, we add H plus, so it becomes HNO3. Let's take one more example here. Like, suppose I'm taking Na2CO3. So it contains sodium ion, which comes from a base part, carbonate ion, which comes from an acid part, and on adding hydroxide, it becomes NaOH, and carbonate part, it becomes H2CO3 by addition of H plus ions to it. Let's discuss about nature of salt. The salt we are having here, that one is inorganic salt. Have electrostatic type of bond. Water soluble salt we are taking. White, that is the given salt do not have any specific color. Few salts have characteristic smells, like ammonium salt, they have ammonical smell. Acetate salts, they smell like a vinegar. Sulfide salts have rotten egg smell. Choice of acid for qualitative analysis. HCl. We do not use HCl because HCl gas given out in this case, and in the presence of HCl gas, actual gas cannot be identified. Also, we can't use nitric acid because it is a strong, or you can say powerful, oxidizing agent. So in order to detect radicals, we either use dilute sulfuric acid or a concentrated sulfuric acid. That depends on the decomposition of ion. Like, few ions, few radicals, carbonate radical, sulfide radical, nitrite radical, these are easily get decomposed in presence of dilute sulfuric acid. So we use dilute sulfuric acid too for the analysis of these radicals. And few radicals like chloride, bromide, nitrate, acetate, iodide, these radicals are detected with the help of concentrated sulfuric acid. Like in dilute sulfuric acid, we have carbonate radical, which in presence of dilute sulfuric produces carbon dioxide gas. A brisk effervescence is produced. in this case. Next radical, we have a sulfide radical, which when comes in contact with dilute sulfuric acid, it changes into hydrogen sulfide, having a rotten egg smell. Then we have a sulfide radical here, which on reaction with dilute sulfuric acid gives sulfur dioxide gas having burning sulfur smell. In case of concentrated sulfuric acid test, we have chloride radical, which changes into HCl, white fumes, and these white fumes get intensified when this comes in contact with the ammonia. Bromide produces bromine gas, reddish brown gas. Iodide, that produces iodine, deep violet peppers. Nitrate produces NO2 gas with concentrated sulfuric acid, which is brown gas. And in order to intensify this nitrogen dioxide gas, either we use a paper pellet, which acts as a reducing agent, or we use a copper turning here. Acetate radicals changes into acetic acid. Acetic acid vapors are produced in this case, vinegar-like smell. A quick tip, both carbon dioxide and sulfur dioxide, they both turn lime water milky. Both turns lime water milky. Then how to identify whether the gas produced is carbon dioxide gas or a sulfur dioxide? So what we do when this gas, it comes in contact with potassium dichromate paper. If this paper, it turns green, then the gas is sulfur dioxide gas. In case of carbon dioxide, there will be no change in the color of potassium dichromate, which is originally orange in color. In a similar manner, both nitrogen dioxide and bromine gas, they are brown gas. Then how to identify whether the gas is nitrogen dioxide or it is bromine? So what we do, we identify this with the ferrous sulfate here. If the ferrous sulfate is originally green in color, and if this ferrous sulfate paper, it turns black, then the gas will be nitrogen dioxide, and if there will no change in the color of the ferrous sulfate, then the gas is bromine gas. Formula of few important reagent. Nessler reagent, its formula is K2 HgI4. Coordination part is HgI4 here. Potassium ferrocyanide K4 FeCN6. This FeCN6, this we keep in a coordination sphere, and iron Fe, it is present in +2 state here. Sodium nitroprusside Na2 FeCN5NO. Lime water CaOH whole twice. Let's discuss chemistry of few important chemical tests. So first one I am taking here is a ring test, which we do or perform for a nitrate radical. So let's start. First, we take salt solution in a test tube, which is prepared by adding a water to a salt. Then to this we add freshly prepared solution of ferrous sulfate. Why I am taking a fresh solution of ferrous sulfate here? Because otherwise it get hydrolyzed. To this we add concentrated sulfuric acid along side wall of test tube. This results in the formation of brown ring at junction of two solution. Please do not mix the reaction mixture here. Its formula is FeNO H2O5. Keep the test tube as such so that the brown ring settle. It becomes stable. Chromyl chloride test. This test we perform for chloride radical. We take a salt in a test tube. To this we add concentrated sulfuric acid, few drops. Then to it we add potassium dichromate, which is orange in color, and then heat the reaction mixture. This result in the formation of orange-red vapors of chromyl chloride gas. To this reaction mixture, when we add sodium hydroxide, it produces yellowish color because of the formation of sodium chromate. And this sodium chromate on reaction with lead acetate it produces yellow precipitate. Sodium salts are water soluble, so a coloration is there, and lead salts are water insoluble, so a yellow precipitate is obtained here, which is of lead chromate. Iodide or bromide radicals, they do not form chromyl bromide or chromyl iodide because of the resulting component is highly unstable. Chromyl bromide and chromyl iodide are unstable. Flame test. Let's discuss chemistry of flame test. We are having salt. To this we add concentrated HCl in order to convert it into a more volatile chloride form. Metal chlorides are more volatile than that of salt, which is a less volatile form. So with the help of concentrated HCl, what we do here, we convert a given salt into a metal chloride form, which is more volatile and gives characteristic color in a flame. Glass rod is not used here because glass rod, it has sodium silicate and it imparts golden yellow color to flame because of sodium. Golden yellow color. Next step. In place of glass rod, we use here platinum wire. Platinum wire is used. It is inert, not react with acid, and most importantly, does not impart any characteristic color to flame. Color shown by various radicals. Brick red, calcium, strontium, crimson red, barium, grassy green, zinc, green flashes, lead, dull bluish white. Common ion effect. This concept we study under ionic equilibrium in our grade 11. So what is a common ion basically? If to the solution of weak electrolyte, I'm simply taking a simplest example of acetic acid here. Organic acid or weak acid. And to the solution of weak electrolyte, a strong electrolyte having a common ion. So the common ion here I am taking the acetate ion, and the strong electrolyte I am taking sodium acetate, salt of weak acid with strong base. So in this case, weak electrolyte, they show reversible reaction in water, and the strong electrolyte, as they get ionized completely, they produces acetate and sodium ion. And if you look at the reaction mixture, then we have acetate ion as a common ion here. Common ion, which is a acetate ion. So in this case, there is an increase in the concentration of acetate ion toward the product side. So according to the Le Chatelier's principle, what happens here, if there is an increase in the concentration of product, then reaction shifts in backward direction. Backward reaction takes place. Why this backward reaction takes place? Because of the increase in the concentration of product, and this maintain constant pH. Let's apply the concept of common ion in a qualitative analysis. Let's discuss about group 2. Group 2 are precipitated by passing H2S gas in presence of dilute HCl. How to make a H2S gas in a test tube? Sodium sulfide with dilute HCl. Then the resulting gas obtained is a H2S gas. So the group 2 radicals are detected with the help of hydrogen sulfide gas in the presence of dilute HCl. Hydrogen sulfide gas, H2S, that one is a weak electrolyte. So it shows reversible reaction, 2H plus and sulfide ions. Whereas HCl, it is a strong electrolyte. So it ionizes completely, HCl, irreversible reaction, and it produces H plus and Cl minus. If you simply check here, what happens basically? There is an increase in the concentration of H plus ion. So the reaction, this reaction shift in the backward direction according to the Le Chatelier's principle, and this maintains the concentration of sulfide ion. So at this lower concentration of sulfide ion for group 2, ionic product that becomes greater than that of the solubility product here. If an ionic product is more than that of a solubility product, then this result in a precipitation of a compound here. So in this case, as H2S gas is passed through the solution in the presence of dilute HCl, the precipitate of group 2 are of sulfide, which are black in color. Now the question is, why the other groups, they do not get precipitated like group 3, 4, 5. Why they are not precipitated as a sulfide here? It means they require large concentration of sulfide ion. So for other groups, if they are not precipitated here, it means their solubility product is more than that of a ionic product. Precipitation takes place only when ionic product is more than that of a solubility product. Let's discuss about group 3, where we have group reagent NH4Cl and NH4OH. NH4Cl, that one is a strong electrolyte, and NH4OH is a weak electrolyte. So in this case, NH4OH undergoes an equilibrium having ammonium and hydroxide ion, and the NH4Cl, it get completely dissociated to form NH4 plus Cl minus. So in a reaction mixture, we have NH4 plus ammonium as a common ion here. So this decreases the degree of dissociation of ammonium hydroxide. So in this case, degree of dissociation of NH4OH decreases as the reaction shift in the backward direction according to the Lee-Chatelier principle. If there is an increase in the concentration of a product, then reaction goes in a backward direction. So as there is a decrease in degree of dissociation of ammonium hydroxide, this also results in decrease in concentration of hydroxide ion. So even at this low concentration, ionic product of group 3 radicals are more than that of solubility product, which result in the precipitation of group 3 radicals here as a hydroxide. So we get metal hydroxide as a precipitate here only for group 3 member. Why so? Because their ionic product is more than that of a solubility product. Other group members like the group 4, 5 do not show or do not form precipitate here because they require large concentration of hydroxide ion. So here solubility product is more than that of the ionic product. As I told you earlier, precipitation reaction takes place if and only if ionic product is more than that of a solubility product. So that's why group 4 and 5 radicals are not precipitated here as a metal hydroxide here because their solubility product is quite high. Let's discuss about group 4, where we have H2S in presence of ammonical solution. Both are weak electrolyte here. So H2S, it produces H plus and sulfide ion. NH4OH, it produces ammonium. None of the ion is common here. But we have H plus and OH minus. These H plus and OH minus combines with each other to form H2O. So in order to have H2O, what we need? More and more dissociation of both electrolytes, as because of the formation of water here, what happens, degree of dissociation of H2S increases. This results in increase in sulfide ion concentration. As the sulfide ion concentration of for group 4 radical is more than that of the group 2, so in this case ionic product is more than having more concentration of sulfide ion, which is more than that of the solubility product, and result in the formation of sulfide precipitate of group 4 radical. Group 5. In group 5, we have ammonium carbonate as a group reagent in the presence of ammonium chloride and ammonium hydroxide. Ammonium carbonate, that one is a weak electrolyte. Ammonium hydroxide, that one is a weak electrolyte, but ammonium chloride is a strong electrolyte here. So ammonium carbonate, it produces ammonium ion and carbonate ion, whereas ammonium chloride, as it is a strong electrolyte, it produces ammonium and chloride ion. So we have a common ion ammonium here. So because of the increase in concentration of product, according to Le Chatelier's principle, reaction shift in the backward direction, this result in decrease in degree of dissociation of ammonium carbonate. As there is a decrease in degree of dissociation for ammonium carbonate, this results in decrease in concentration of carbonate ion here, but that concentration is sufficient enough to make ionic product more than that of the solubility product. Hence, group 5 radicals, they are precipitated out in the form of carbonate. For the precipitation of basic radical, two concepts we majorly use, that is a common ion effect and a ionic product versus solubility. Common ion effect. How to create this common ion? For this purpose, we take a reaction mixture having weak electrolyte with a salt of the same ion as a strong electrolyte. Salt with strong electrolyte. For example, NH4OH, NH4Cl, salt of ammonium with chloride. Principle that is we use here is Le Chatelier's principle in case of this ionic equilibrium. So, according to Le Chatelier's principle, if a reactant changes to product and there is an increase in concentration of product, like in this case, there is an increase in concentration of ammonium ion because of the addition of ammonium chloride to the reaction mixture, then the reaction shift here in a backward direction, shifts backward direction. So, because of the shifting of a reaction in a backward direction, degree of dissociation of reactant decreases. This results in low concentration of anion towards the product side. second concept we apply here for the precipitation of basic radicals in a particular group. That one is ionic product versus solubility product concept. Ionic product, that is the product of ions, which is applicable to all kind of solution, whether that is the saturated or unsaturated at any range of temperature. Whereas the solubility product is the product of the ions in a saturated solution and at a particular temperature. Precipitation takes place only when ionic product exceeds solubility product. Only then the precipitate are formed. As because of the Le-Chatelier's principle, there is decrease in concentration of anion. At this low concentration, ionic product becomes more than that of a solubility product for a particular group, and this result in the formation of precipitate. Other group members, they do not form precipitate. Other groups, they do not form precipitate. It means they require high concentration of anion. So in this case, solubility product is more than that of a ionic product. Which simply take an example here of group 2 and group 4. In group 2 and group 4, we have H2S gas as a group reagent. But the group 4 radicals are not precipitated out in group 2. Why so? Because they require quite high concentration of sulfide ion, which is possible only in case of group 4, where we have a reagent H2S in a presence of ammonium hydroxide, which result in the formation of water there, and this result in increase in degree of dissociation of H2S. That's why group 4 radicals are not precipitated out as a sulfide in case of group 2. So in case of group 2, if we are talking about group 4 radicals are not precipitated there, it means at that time their solubility product is more than that of ionic product. But when you are using H2S gas in presence of ammonium hydroxide, ammonical solution में we are adding H2S gas, in that result in increase in concentration of sulfide ion, which is sufficient enough to precipitate group 4 radicals.